Hello and welcome. Today we're diving into a classic physics puzzle that's all about finding balance, but with, well, an electric twist. We're talking about electric charges.
So here's the challenge for today. We've got two electric charges, and we need to find that one single, perfect spot where a third charge would feel absolutely no net force. Where could this sweet spot of perfect balance possibly be?
Okay, let's jump right in. First things first, we need to set the scene for our problem.
Let's meet our two main players. On the left, we have a positive charge, we'll call it Q1, with a value of plus Q. And 5 centimeters to its right, we have a negative charge, Q2, which is 4 times stronger, with a value of minus 4Q. These two are locked in place.
Our goal is to find what's called the equilibrium point. This is the sweet spot where, if we place a third charge, let's call it Q3, the pushes and pulls from our two original charges will perfectly cancel each other out. The net force on Q3 would be 0, and it would just float there, in total balance.
Now, before we even think about writing an equation, let's play detective. There are 3 possible regions where we could place our third charge. Let's analyze them one by one.
Our first area of interest is Zone 1, the space directly between our two charges, Q1 and Q2. Let's imagine we place a positive test charge, Q3, right there in the middle. And here's where it gets interesting. Q1 is positive, so it repels our positive test charge, pushing it to the right. Meanwhile, the negative charge, Q2, attracts our positive test charge, pulling it also to the right. See the problem?
Exactly! The two forces are teaming up, both pointing in the same direction. There's absolutely no way they can cancel out to 0. So this entire zone is out. It's impossible to find equilibrium here.
Let's move on to our next suspect, Zone 2, the region to the right of our stronger negative charge, Q2.
Okay, at first glance, this looks a bit more promising. Q1, being positive and far away, gives a little push to the right. Q2, being negative and close, gives a strong pull to the left. The forces are in opposite directions. That's a good start.
But here's the catch. In this zone, our test charge Q3 will always be closer to Q2, the stronger charge. Because of that proximity and its greater strength, the pull from Q2 will always overpower the weak little push from the more distant Q1. So once again, no equilibrium possible. Zone 2 is a dead end.
Through a simple process of elimination, that leaves only one possible place left to look. This has to be the one.
Let's examine our last hope. Zone 3, the region to the left of our smaller positive charge Q1.
And look at that. Once again, we have opposing forces. The positive charge Q1 repels our test charge, pushing it to the left. The negative charge Q2 attracts it, pulling it to the right. So the directions are correct for a cancellation.
And this is the key to why this zone works. Our test charge is closer to the weaker charge Q1. This means the stronger pull from the more distant charge Q2 can be perfectly balanced out. Q1's weakness is made up for by proximity. This is the spot. We found our region.
Okay, on to the math. We figured out conceptually where the equilibrium has to be. Now let's find the exact location.
So the crucial point is this. For equilibrium, the magnitude of the force from charge 1 on charge 3 must be exactly equal to the magnitude of the force from charge 2 on charge 3. And to calculate those forces, we use the famous Coulomb's law.
We start with the full Coulomb's law equation, setting the force from Q1 equal to the force from Q2.
Let's call the unknown distance d. Now, watch how nicely this simplifies. The constant k and the test charge Q3 cancel from each side, which is interesting because it means the value of our test charge doesn't even matter. Then, the base charge Q also cancels out, leaving us with this much simpler final equation that's all about the distances.
After rearranging that last equation, we get this beautifully simple expression to solve. The quantity d plus 5 squared divided by d squared equals 4.
And we're at a really important step in the algebra. To get rid of those squares, we have to take the square root of both sides. But remember, whenever you do that, you have to account for both the positive and the negative roots. This means we're going to get 2 potential mathematical answers.
Math might give us 2 solutions, but the laws of physics will tell us which one actually describes our reality. It's time to interpret our results.
Let's solve for both cases. When we use the positive root, plus 2, we solve the simple algebra and find that d equals 5 centimeters. That's a positive distance, which makes physical sense. But when we use the negative root, minus 2, we get d equals negative 5/3 of a centimeter.
Since d represents a physical distance in our setup, it can't be negative. That second solution, while mathematically valid, is physically meaningless for our problem. So we reject it, which leaves us with our final answer. The equilibrium point is located exactly 5 centimeters to the left of the first charge, Q1.
And there you have it. A combination of logical deduction and some straightforward algebra leads us to the answer. But it does leave us with a fascinating question to ponder. What if our starting charges, Q1 and Q2, had both been positive? Where would the equilibrium point be in that case? Something to think about.